introduce Aisley Milstead, Ash, right, who is a student, a PhD student in the group of Tobias Osborne at the University of Toronto. And he will be telling us about tensor network states for non-abelian games here.
Okay. Yeah, thanks very much for the invitation as well to GIPHY. So yeah, I'm going to be talking about tensor network states for non-abelian gauge theory. The content will be first a little bit about quantum fields, in particular on lattices. And then I'll move on to just running through a few tensor network state ansatzes and methods. And then I'll get to the real meat of this, so a ground state ansatz for Yang-Mills theory on a lattice. So quantum fields. Well, obviously, they've been hugely successful, and the Standard Model is probably the most fundamental theory that can be tested that we have. One of the main tools in quantum field theory is, of course, perturbative scattering theory, which is where most of the well-known results from QED come from. You can use it to look at the high-energy behavior of quantum chromodynamics, because the effective coupling between quarks becomes weak at high energies. But there are also many important non-perturbative phenomena. So the low energy, the IR behavior of QCD, where we're interested in why and how quarks are confined, and generally in the hadron spectrum. So the kind of particles that exist in this theory. So there are at least a few methods which exist for looking at these non-perturbative phenomena. For example, the strong coupling approach in lattice QCD. So you put QCD on a lattice, and you can perturb around the strong coupling limit, and you can learn quite a lot about how confinement, at least in that limit, functions. And of course, there are Monte Carlo simulations, also of lattice models. And recently, huge Monte Carlo simulations with enormous computing clusters have done an excellent job of determining from first principles the masses of lower energy hadrons from QCD, which is really impressive, of course. Working on a lattice is, of course, a really nice thing to do because it gives you a natural momentum cutoff. You avoid divergences. So let's have a look at an example of a simple field theory on a lattice. So if we take the real scalar field with a quartic interaction, so known as 5^4 theory, you have a classical continuum action given by this thing up here. If you set lambda to 0, then the solutions are plane waves, and you have the free theory. Now you can discretize this in space. We'll just discretize space and not time, and go to the Hamiltonian picture, and you get something like this. So this derivative term becomes this finite difference, and also is hidden inside this conjugate momentum operator. And again, if lambda is 0, the solutions are plane waves on a lattice, only now you have a momentum cutoff. Now, what's the Hilbert space for this guy? Well, it's a product over the lattice sites of L2 of R. So you've essentially got a series of harmonic oscillators here. Now, if you want to study this numerically, you want to go to a different basis. You can go to the number basis and cut off at some finite number. And then this just becomes a many-body spin system. And you can, for example, apply DMRG to it and do all sorts of interesting things like that. But then the question is, how do you get back to the continuum? How do you do a continuum limit? Well, one way of relating a lattice theory to a continuum is to look at the correlation length. So in the case where the continuum theory is gapped, there's a finite correlation length in the continuum, which you can measure in meters, for example. And of course, the correlation length in terms of lattice sites of your lattice theory should be related to this physical correlation length via a scaling factor, which is your lattice spacing. So you can play with your quantum theory. You can shift the parameters in the Hamiltonian, lambda and the mass in this case. And each time, maybe you can calculate your lattice correlation length, and you can use this matching up to get a value for your lattice spacing. And once you identify which parameters affect the lattice spacing in this way, you can take a continuum limit. Of course, you should also be adjusting other parameters in a certain way following an RG flow, but the basic principle works like this. This is sometimes called dimensional transmutation, this business of getting the lattice spacing from the correlation length like this. Okay, now let's have a look at some tensor network state methods. So tensor network states parameterize the low entanglement corner of Hilbert space. The hope is that the physically relevant states, the one you're interested in, lie in this corner. So, for example, ground states of local Hamiltonian systems in many cases. You can choose how much of the Hilbert space you encompass by adjusting the bond dimensions d, which are the dimensions of the tensors in the tensor network. So the simplest example probably is matrix product states, where you write, well, they're called matrix product states because the state coefficients in some chosen basis consist of matrix products, where there's a matrix or a set of matrices for each lattice site on the chain. They can be visualized as a tensor network. So this just represents the matrix multiplication that's going on here. So this outer sum over the physical indices is actually hidden here. The physical indices are these blue dangling things underneath. And you can imagine a ket being glued on to the bottom here to represent the sum connecting these things to the ket on the right here. And the matrix indices are represented by the horizontal legs here. Now, you can use these things, tensor network state ansatzes, as variational classes, of course. You can take the matrices, the tensors, and use them as parameters and optimize over them. So look for minima in the energy, for example. And there's been a lot of success in doing that, particularly in condensed matter. So the DMRG method minimizes the energy by sweeping across the chain and minimizing each tensor in turn, or pairs of tensors in the two-site method. It can be applied to finite and infinite systems, and it's really great at finding ground states. If you want to evolve in time, you could use the time-evolving block decimation method, TEBD, which is also in infinite and finite variants. It exploits a trotterization of the Hamiltonian to update the MPS in a way that does not explode the bond dimension, and you can truncate again afterwards to get back down to a lower bond dimension if you wish. There are also the so-called tangent plane methods, which exploit the tangent vectors to the manifold formed by the matrix product states. If you take care of the gauge freedom in the MPS representation properly, then this behaves really nicely. And there are a few methods implemented on the back of this. For example, the time-dependent variational principle you can implement using this, which allows you to evolve time or evolve in imaginary time. You can represent the gradient with respect to the energy on the tangent plane, and then you can implement gradient minimization methods like the nonlinear conjugate gradient method. And the tangent plane also provides a natural place to look at excitation. So if you find your ground state, then the tangent plane contains small perturbations around the ground state. And in fact, the tangent vectors of MPS look like local perturbations on your ground state. So it's a natural ansatz for excitations in many settings. We've implemented a bunch of these tangent plane methods in a package called EvoMPS, which is programmed in Python. It's open source. It's on GitHub. If you're interested in using that, or you want to ask me questions, please ask me later. This is a little advertisement. Okay. But there have been many successful applications of MPS techniques in general, not only in condensed matter physics. So just to take a few, you can apply them to anyonic systems where you have, so for example, a chain of anyons where you have some non-trivial local constraint on your Hilbert space, which is quite closely connected to the problem of looking at gauge theories. You can look at open systems, not just closed systems as well. But you can also look at quantum fields, and that's what we'll get to in the next section. So, of course, there are important generalizations of MPS, for example, to higher dimensions. So the projected entangled pair states, PEPs, are initially a fairly straightforward generalization of this tensor network into more dimensions. 2D is the most popular because then you still have kind of a hope of calculating things and contracting this tensor network. There's been a lot of success using that method. There's also the MERA multi-scale entanglement renormalization, ansatz, where you build in the idea of state renormalization into a tensor network to, for example, efficiently represent 1D critical systems, among other things. Okay, so applications to QFT. Well, for example, that simple field theory we looked at before, in 1+1 dimensions, it has a symmetry breaking phase transition. And the location of this phase transition is away from classical limits, so it's a non-perturbative phenomenon. So you need numerics, or well, numerics is one way of tackling that problem, finding its location. You can use Monte Carlo, but you can also use DMRG or MPS to do that. So this is a continuum limit finding this critical parameter. There's also been work on lattice gauge theories. For example, with MPS in one dimension. Sorry.
Can you go back?
Yeah, sure, of course.
Can you explain this plot? What is it?
Okay, so this is the lambda parameter, the coupling parameter for 5-4 theory, and this is lambda over this renormalized mass parameter squared. So because of the way, so these lambda, the tildes mean that I put these parameters in lattice units. So you can see that if you take lambda and mu to 0, you go to the continuum because they're just scaled with the lattice spacing. So you could choose mu here, but I've chosen lambda. So if you take lambda to 0, then you can sweep in mu and find the phase transition on the lattice. And if you do this for smaller and smaller lambda, then you hope to approach the phase transition in the continuum limit. And yeah, this has been known as I say, with Monte Carlo techniques as well, and the values actually agree very nicely.
So is this plotting both Monte Carlo and matrix product state results? Or?
This is just MPS results. So these are two different ways of determining the lattice critical point by looking at the scaling of different quantities. So one, the energy gap, which is nice in this model, it's basically an Ising model, or well, it's in the same universality class, so the gap scales linearly, and that's these red points. So it's easier to.
Do you have anything to say about doing the same with continuous matrix product states, where you would not have to take this continuum limit?
Well, so okay, the numerical techniques there are a little more complicated and harder to implement. That's one thing. But okay, so with CMPS, I'm not an expert on CMPS, but I'm told you would still need to introduce some kind of. So you've got a natural cutoff with MPS, a natural momentum cutoff. With CMPS, you would need to introduce that in some way. And if you have to do that anyway, you might as well just go on the lattice. That's kind of one way of looking at it, at least. Okay. So yeah, MPS has been applied to one-dimensional QED, also known as the Schwinger model, with quite a lot of success. So for example, it's been looked at with a constant background field, and you can see spontaneous pair creation going on in that situation. You can look at the real-time dynamics of this. This is something you cannot do with Monte Carlo techniques because they are restricted to Euclidean space. You've done a Wick rotation, and you can approximate some dynamical properties, but you're basically restricted to ground state properties. So that's a nice advantage of using tensor network states. There's been work on MERA for lattice gauge theories. So far, focusing on discrete groups and relating it to the toric code, which is a lattice gauge, which is related to a lattice gauge theory with the discrete group Z2. And there's been work on PEPs for lattice gauge theories, also with a view to looking at continuous groups, but truncating them in some way applicable for doing numerics. So, okay, we basically come to the point we wanted to get to. Now we're discussing lattice gauge theory. So let's look at that in a bit more detail. Yang-Mills theory and the Kogut-Susskind Hamiltonian. So in the continuum, the classical action for Yang-Mills theory looks like this. The field strength tensor goes in. This is the non-abelian field strength tensor where the G is a coupling term which goes onto the non-abelian part. So the abelian case is a free theory. It's pretty boring. But the non-abelian case of this pure gauge theory, where we don't have any matter, is totally non-trivial and yeah, unsolved. So you can discretize that theory, and if you discretize it just in the spatial direction and leave time continuous, you can go to the Hamiltonian picture, in other words. You get, or you can, well, yeah, one of the simplest Hamiltonians you can write down is the Kogut-Susskind Hamiltonian. This consists of a kinetic term, this term on the left, also known as an electric term, and a potential term, this term on the right, also known as a magnetic term. So the electric term acts on edges. It's just a sum over operators acting on edges, and the magnetic term acts on plaquettes. And there's a coupling parameter G, where GH is used to distinguish it from the continuum coupling parameter, which is something different in general. In the strong coupling limit, you only have this first term, and you can see already that the state will be a product state over the edges because you just have these edge terms here. In the weak coupling limit, there should be the only phase transition of this model. This is not known with, well, this is thought to be the case, that the only phase transition occurs when G goes down to 0. And at this phase transition, the lattice correlation length diverges. And so you can think of this as taking a continuum limit in the sense I discussed previously. So what's the Hilbert space look like? So I said the degrees, well, I said that these operators act on the edges. It's like the toric code. The degrees of freedom act on the edges. Classically, you have gauge group elements on the edges. In the quantum case, you have the Hilbert space L2 of the gauge group on each of the edges. You can write wave functions or states as wave functions in terms of a position basis on these edges, where you integrate over the Haar measure for the group. So that's not the only basis, though. There's also a really useful momentum basis, or Fourier basis, given by the Peter-Weyl theorem. So the Peter-Weyl theorem tells us that the irreducible representations of the group form a basis for L2 of G. So we're summing here over irreducible representations labeled by L. So we're summing over spin 0, spin half, and so on in SU2, for example. And these two vector spaces correspond to the left and right matrix indices of the irreducible representations. And this is a nice bipartite structure, which is really intuitive for this gauge theory. So if we expand a wave function in terms of this basis, which I've done here, you sum over the irreps and the matrix coefficients, and you have your Fourier coefficients here, psi hat. And we can write the left and right matrix coefficient indices as left and right parts of this bipartite pair. And we associate the left matrix index with the start of a link and the right matrix index with the endpoint of a link. This makes a lot of sense, especially when we consider how gauge transformations act, which we'll look at in a second. So the lattice now looks like this. We've expanded our vertices to take into account that they consist of all these start and end points. So how do gauge transformations act? Well, to implement those, we need to know how to do group rotations in the Hilbert space. So for that, we define these left and right rotation operations. These are unitary operations. So L multiplies from the left. This is in the position basis. R multiplies from the right with the inverse. How does this apply to gauge transformations? Well, the gauge transformation is classically, well, and quantumly, is an element of the gauge group assigned to each vertex in the lattice. And in the classical case, you just have elements of the gauge group living on the edges surrounding. And the gauge transformation consists in multiplying those elements from the left or from the right, depending on whether it's the start point of the edge or the end point of the edge in the vertex. So you can implement this with these left and right rotations by just here using a left rotation, here using a right rotation, and so on.
Sorry, Ash.
Yeah.
So your Hilbert space is the tensor product of vector spaces attached to each edge.
Yes. Yeah, exactly. Yeah.
And so in this graphical representation, what you are doing is every segment here represents a local Hilbert space.
Yes, every edge is the local Hilbert space.
And the two dots, so the arrow is just telling you what is the left and right part of
Yeah, yeah. And so,
It's telling
exactly.
you how the gauge transformations are going to act in that.
Yes, yes, indeed, yeah. So yeah, exactly. You can think of, so the way the lattice is shaped and the way gauge transformations act, this is more or less the same thing. So if you define how your gauge transformations act on your Hilbert space, you define the shape for your lattice. You've defined how the graph is connected. Okay, so there are a couple of simple gauge invariant states here. If we take the really simple graph of a single vertex and a single link just looping in and out, how do gauge transformations act on that? Well, in the wave function picture, this x element of the gauge transformation just multiplies from the left and from the right. So any gauge invariant wave function has to satisfy this property, which means it's a class function. Now there's a couple of simple examples, but the one of states that fulfill this property, but the one we'll look at is where we're in a position eigenstate of the identity operator. And you can convince yourself that that satisfies that property fairly easily. So this is, in the wave function notation, just a delta function. We're going to use that because if you were to put a plaquette term from the Hamiltonian on this really small plaquette, then you would have minimized the potential term of the Hamiltonian. The other gauge invariant state we'll look at is the dangling link. So this dangling link, you can see, has to be decoupled from the rest of the graph. This is because gauge transformations can act just on this dangling vertex, for example, with no correlation with the rest of the graph. So we can perform arbitrary rotations on this link. So if the thing's going to be gauge invariant, it can't be coupled to the rest of the graph. And indeed, it has to be in the equal superposition of all position elements, so in the momentum zero state, corresponding to the trivial representation within the space of irreps. So in the notation, in the bipartite notation from before, this is the 0, 0th matrix element of the 0th irrep. Yeah.
So on the left-hand side, psi is the wave function. Or
yes.
Function, or however we have to call it.
Yes.
For that link.
Yes, for this edge, yeah.
For the edge.
Yeah.
What about on the right-hand side?
On the right-hand side, we're also just talking about this edge because it has to be in a product state with the rest of the graph. So we only need to consider that edge.
Right, that's the conclusion you wanted to reach.
I wanted to convince you that this is a gauge invariant wave function for that edge. And I also wanted to convince you that it has to be decoupled, but right. Yeah.
But psi is already only referring to that.
Yes, indeed, yeah. Yeah, so I was just considering the state of this edge. The rest is something else, but it doesn't matter. Okay, so with these basic tools, we can now manipulate the graph by performing a kind of quantum parallel transport. Now, the tools we use to do this are controlled rotations. So I'm going to define here controlled left and controlled right rotations. And so parallel transport is moving something along the graph. If we use as the control systems for these operations the existing edges on a graph, and we use something else as a target, some particle we want to move, then these quantum operations will perform that parallel transport in the Hilbert space. We're going to use as targets objects that transform under the fundamental representation of the group, so the same representation as the edges. In fact, we will be moving edges around using these operations, so manipulating the graph. Let me explain a little bit what I mean. So you can see why these operations manipulate the graph if you look at how they act on gauge transformations. So here, on the right, I've got a simple case of, well, I'm not going to consider these connections to the rest of the graph here. I'm just going to consider this horizontal link and this loop here. Now, let's consider a gauge transformation which acts on the right vertex. So that's implemented by Lx acting on this central edge. Okay. Now, what I'm going to do is I'm going to transport the source end of this loop along this edge to the other vertex. This is done, as I was saying, by using a controlled rotation with the existing edge as a control. And if I do this operation on the gauge transformation acting here, then I see the result is that L of x is now acting on both the control and the target. The target was this edge here. So we can see that it's consistent with this bottom picture where the gauge transformation at x now acts on both of these edges. Okay, I'm going to illustrate. Before I do that, I want to say these basic moves have been used before. For example, by John Byers in a paper on spin networks. They've been used in the discrete gauge group case by Aguado and Vidal for looking at the mirror for the toric code, and they've been used in a few other contexts as well. Let's look at some simple cases of how we want to use this. So let's say I want to add an edge to an existing graph. So the existing graph of this is this rectangular plaquette here. And the first thing I want to do is tensor on a gauge invariant state. So I form a tensor product of the previous state and this new loop, which is in the identity position eigenstate. Then I'm going to use these controlled rotations to move first the starting point of this edge along here horizontally and then up to the middle. So that's controlled rotation first with the control, this vertical edge, and the target, the new edge E. And then the same for 2, so I get CL2E, CL1E. And then to move the endpoint with a right rotation, acting from the right, up to the middle, I just do a controlled right rotation over this 6 edge. Okay, so that's edge addition. When doing this, we're, of course, entangling this new loop with the rest of the system. It was in the product state, but it's going to be highly entangled with the rest of the state after we've done this operation. Another thing we can do is subdivide an edge. So if we tensor on now, instead of a loop, one of these dangling edges, we can integrate it into the graph by transporting the endpoint of an existing edge in the graph along the new edge. So we're just moving it up there, using a controlled left rotation, this time with the control as the new edge and the target as the old edge. Okay, so we got 2 basic operations, edge addition, edge subdivision. Those are going to form the basis. Sorry, yeah.
What were you about to say? I was going to ask you what the context is for doing these moves. Is it to repair initial state or something?
It's going to be, these are going to form the basis of a fine graining operation. So yeah, I'll get onto this now.
Can you elaborate on what these basic blocks, what are they accomplishing? I mean, what does it mean to have flat an edge, or what does this mean?
Well, so you're adding additional degrees of freedom to your system, and you're entangling them with the system by
compatible with some rules, right? So
yeah. So there's freedom in how you do this, of course, at the moment.
These rules accomplish something concrete.
Oh, yes, of course, yeah. Okay, I should have stressed this. So what's really important in this whole process, all these operations preserve the gauge invariance of the state. Okay, that's crucial, yeah.
It's just a relabeling of your sites, finally.
Sorry?
Does this just mean you're relabeling all sites, kind of? Just shifting around sites?
Yeah, exactly.
Making a new labeling.
That's all we're doing. Yeah, so we're really reshaping the graph because we're changing how the gauge transformations act. So the gauge transformations kind of define the geometry of this graph, well, the connectivity of this graph. And because we're manipulating those, we're changing that connectivity. They also have effects, of course, on the terms in the Hamiltonian. So they're going to move plaquette terms around. They're going to move these edge terms around in interesting ways.
So then the basic idea is you have some lattice and some degrees of freedom on the lattice, in this case on the edges.
Yes.
And you have a wave function which is gauge invariant.
Yes.
Now you're explaining how to add new degrees of freedom in the form of new edges.
While maintaining this gauge invariance. Yes.
Is that, I mean, it's just gauge invariance, or is there something else?
So far it's just gauge invariance. Okay. Yeah, so far. But yeah.
Is that final state? So are you saying that gauge invariance gives us a complete specification of the state? I mean, it seems that you tell me how the edges are connected.
Yes.
That already specifies the wave function. Is that what? Is the wave function completely specified?
By how the connection? No. No. So there's a gauge invariant subspace which contains a bunch of states, but we're working within that gauge invariant subspace by using these gauge invariance preserving operations. So so the state you get out of this is going to depend a lot on the initial state and exactly how you decide to do these operations. So, for example, the path you take will affect the state in the end. Whether it affects gauge invariant expectation values is another question, but it will affect the state.
But basically, you need to choose a state of the loops.
Yes, that's one choice you have.
That's
Yeah.
the choice.
You mean the new loops that you introduced?
So I took a specific state for this loop, but if I add multiple loops, for example, they can be entangled with each other, and they can be in other states. That's no problem at all.
But you don't need to use a delta function.
No. I'm choosing this delta function for a reason, which will hopefully become a little clearer later. Okay.
I'm sorry, I'm just curious. I'm sort of a random particle person who got here.
Okay.
And I think of the states in Kogut systems simply as electric fluxes on the lines. That could be a basis of states. How is this related to that?
Sorry, say that again.
If you have closed electric flux lines,
yes.
basically product of link fields on closed loops,
yes.
Those are gauge invariant states.
Yes.
So how are these states related to that description? And how are these moves related in that language? Because I'm totally not familiar with that, but I thought I understood Kogut system.
Oh, okay. Well, I mean, okay, so if you...
and that's a fine basis, and the strong coupling limit gives you confinement and all of that.
Yes.
Nice. Yeah. So
yes.
How are the two things related?
Okay, so maybe it'll help when I show you what the ansatz is in a second. But okay. So essentially, we're going to start with the strong coupling state, which is known as just the product state over the edges, and we're going to use these moves to make a new state, and that new state is going to have a special property, and it will hopefully be close to a ground state of the Kogut-Susskind Hamiltonian for a different value of the coupling. That's going to be the plan. So maybe maybe that will answer your question at least partially.
So, excuse me?
Yes.
Can you show us what CA operator is?
Say again, please.
How does that moving operator?
Control operator.
How does it look?
Yeah.
It looks like this. So it's a controlled rotation in the sense you're picking up the position from this control system here, and you're doing a rotation by that gauge group element on your target system. So you can imagine it in a discrete case. If this is a sum and this is 0, 0, and then 1, 1, then in the 0, 0 case, you're performing a spin flip in one direction, and in the 1, 1 case, you're performing a different operation. So you can imagine it as being, you don't need to worry about the integral, for example. Does that help?
Not yet.
Okay. L and R are these left and right group rotation operations. So they act on a position basis by multiplying with an element of the gauge group from the left or from the right.
So that won't help a random particle person, right?
Yeah.
It's the continuous version of a controller.
Yes.
This was the telescope. Right?
Yeah. Okay. Where were we? So let's get to the actual ansatz. Hopefully this will help bring in some context for all this stuff. So the ansatz will be a non-variational tensor network ground state ansatz for lattice Yang-Mills theory. And it's going to have a few properties, or at least this is the list of properties we'd like to have. It's going to be manifestly gauge invariant. All these operations we've looked at preserve the gauge invariance of the state. It's going to be a contractible tensor network, which means we hope to be able to actually calculate things. It's going to have a Lorentz invariant continuum limit. And the errors that we make in reaching this continuum limit are going to be irrelevant in the sense of the renormalization group. So we want to capture the large-scale physics here. We're not worried about ultraviolet details. Okay. So what is the ansatz? The ansatz is basically a kind of fine graining. So what we're going to do is we're going to start in the known product state strong coupling limit of the Kogut-Susskind Hamiltonian, and we're going to fine-grain our graph in such a way as to favor this potential term in the Hamiltonian. So this is going to be what determines exactly how we use these graph manipulation operations. We want to manipulate the graph, add degrees of freedom, and build them in such a way as to minimize this curvature term, this magnetic term, at the expense of the electric term. Yeah.
Is there a unique way of doing that? Because usually when you do coarse graining, you're basically chopping off information, but here
Yes.
you're fine graining, you're adding more degrees of freedom. How do you know if you're doing it right and you're not adding unuseful information?
Well, the argument is that we're fine graining in such a way as to specifically minimize this term. So this is the physical motivation. So we're interpolating. We're going for flatness in the sense of this curvature term, and we're obviously going to be sacrificing the minimality of the first term when we're doing that. There are multiple ways of fine grading in this way, but depending on the shape of the graph, for example. But there should be an optimal way, if you choose the geometry of your fine graining operation, there should be an optimal way of minimizing that term. So that's what we're going to hold on to. That's what's going to determine exactly how we do this. Yeah.
And your fine grain, can you make the jump even smaller than on the cross grid? Or can you only hope to get it equal?
Say again, make the jump?
When you go from the cross to the fine grid, can you make the term smaller than it was on the cross grid, the respective term on the cross grid?
This term?
Yes.
Yes. In the strong coupling state, we're basically as non-flat as possible. You know, we're really, this term is large, but because the coupling is infinite, then this term in the Hamiltonian drops out anyway. So this term is going to be large, and yes, we're going to, with each step of fine graining, make it smaller. That's the plan. Yeah.
So then, suppose you succeed and you build this wave function, which is a refined version of your starting point.
Yes.
So what's the claim that this is a good, or you hope that this is a good answer for the wave function?
For the wave function, which is the ground state of this Hamiltonian for a smaller value of the coupling. For a smaller value. So we start with G infinite and we go to smaller and smaller couplings. We're going to make errors because obviously we're not caring about this term, we're just trying to minimize this one. But the argument is these errors will not be relevant for the large scale physics. But we also have a way of correcting these errors should they turn out to be relevant, for example, or to get even closer to the ground state.
If you manage to iterate long enough, you are getting closer and closer to what?
To the continuum limit. So I argued before that because there's a phase transition in the Kogut-Susskind model at G goes to 0, and we think there's not one before that, then as we go to G is 0, we will approach this phase transition. The correlation length will get larger and larger, and we'll go towards the continuum.
But how do you change G?
Sorry?
How do you change G? Is it just a parameter? Or
so what we'll have to do is we'll have to match up G to the state that we get after this fine graining operation. So after we fine grained, we'll have a certain correlation length which we can calculate, and then we're going to match that up to a G. That's the idea.
And A gets half after you fine grain, or?
Not necessarily. No, not necessarily. I mean, yeah. It looks like it should, but no. Yeah.
Fine graining, is that something that you do locally with each plaquette, or does it involve a global operation?
It's a product of local operations on plaquettes.
And do you need to do a correction step afterwards? I mean, you do all these independent local steps, and is there some global minimization you do afterwards?
We can do an optional local correction step, which is again a product of local unitaries. That's the plan. So, yeah.
Maybe I don't understand, but people talk about this Rotherning transition when you're trying to get from the strong
yeah.
continuum limit. Do you have anything to say about that?
Yeah, so it's possible this will be an obstacle if we just do these fine graining steps. This is where a correction step where the correction step will actually be using the Hamiltonian and doing an approximate adiabatic evolution back down to as close as you can get to the exact ground state after each step. So if that works, then we should be able to deal with the roughening transition. So as far as I'm aware, the roughening transition is not a full quantum phase transition. It's not, the gap doesn't close, as far as I'm aware. So if we have that correction step, we should be able to deal with that. Okay, yeah.
If you don't have that correction step,
yeah,
then is it correct to think that if you now try to apply RG on the final wave function, you will just end up with the initial state? So, so you have.
You mean if you go back up?
Yes.
Yeah, and
I mean,
coarse grain. Yeah.
If coarse graining corresponds to going to low energies,
yes,
large distances,
yes,
you already know what you will find at that point, right?
Coarse graining, you should get back to strong coupling.
Right, and is that interesting? I mean, is that, you know, is that an interesting wave function?
The strong coupling wave function.
No, the low energy limit of the wave function you just built after all these efforts.
Oh well, yeah. That's yeah. We're interested in we're interested in the ground state and the low energy spectrum.
Right, but you already have an indication of what type of wave function you are going to obtain in the end.
At very large scales.
Yes.
Yes. Okay. So we know the behavior at infinitely large scales. This is the strong coupling behavior. Yeah.
So if you introduce then these corrections, is the low energy large distance wave function that you would obtain at the end of the process still this one?
No, it's going to be something else. So because we're zooming in. Well, okay. So what are we going to get? We're going to get. It's definitely not going to be that one.
Right, but is it in the same universality class? Is it the same phase?
Yes, it will be in the same phase. Yeah, we want to stay in the same phase. So it's thought that in the continuum theory also, there's asymptotic freedom. That's the idea. There's a phase transition at zero coupling for the continuum theory too, and there is presumably not one at any other point. And yeah, so the strong coupling limit should be in the same phase as the as intermediate coupling states, also for the continuum theory.
So you're not very happy with the long distance properties that you have in the wave function. You just want to see that this is connected.
Yes. So yeah. So if you start in the weak coupling limit, for example, then you will be in a different phase. You're in a free theory, and you don't have this confinement behavior. So we'd like, for example, to be able to see confinement going as we zoom in, as we go towards the continuum. Okay. All right. So okay. So how does this actually work? The first step to doing this is to look at a classical interpolation problem. So if you take now in the classical theory some plaquette and you want to subdivide it, so that the curvature term, the magnetic term of the Hamiltonian is minimized over the new plaquettes, then you have to optimize these new links, this A0 to n-1, and you can solve this problem. So this is the second term in the Hamiltonian, and these are the extrema in terms of these A. So there are n different solutions chosen by this integer k. This phi is the flux, is related to the flux through this original plaquette. Now let's look at the solution in a little bit more detail. So this gives you a formula for each A in terms of the original U's, and the flux through the original plaquette is this capital phi matrix here, where we've just diagonalized it with this matrix eta. And you can see from this phi to the j over n part that the flux is being distributed over these smaller plaquettes. Okay, but fine, you can solve this classical problem, but we want to do this in the quantum setting. So let's look at quantum interpolation. So we're going to use the edge subdivision operations and the edge addition operations we just used to do that. So let's say we got a plaquette of the quantum system. It's just a square plaquette. We want to first subdivide the edges with the aim to putting internal vertices in this thing. So we add on our dangling link states on the existing vertices, and we parallel transport the existing links along those to subdivide them and create new vertices in the middle. Now, the dangling link state, remember, can only be in one state. It can only be in this zero momentum state. So there's no freedom in doing that except for, well, where to start, where to put the dangling links, and where to parallel transport them. But we're going to use some scheme. So we'll add 2 dangling links per vertex and integrate them here and here, for example. We'll do that for all of the vertices in the lattice. Now, we want the internal edges. So we're going to add edges in these loop states to these new vertices. And we're going to add them in this position identity eigenstate. And I'll justify that a bit more later. But as I say, if you were to add terms to the Hamiltonian, so plaquette terms for these little tiny plaquettes here, then putting them in the position eigenstate of the identity element would minimize that term. Now what do we do? Now comes now we pull in this classical solution. So the classical solution to the interpolation problem actually gives us effective paths, average paths, along which we can parallel transport these new links. So what we do is we build a new controlled rotation operation. We're going to call it controlled interpolation, where the controls are the external links on the original plaquette, but the targets do not just rotate by those gauge elements on the external links. Instead, we put in these classical solutions. So we put in the solution for A0, A1, A2, A3, and we rotate these target edges according to those solutions. So that means we're effectively pulling these endpoints and start points along these average links into a new vertex in the middle. And in doing so, we will minimize the curvature of these new sub-plaquettes. Okay, so that has determined our fine-graining operation for a single step. This is an isometry. Oh, sorry.
When you do this process of putting new vertices, that generates new terms in the Hamiltonian, right?
Yes.
Are those
yes.
terms the same form as the original Hamiltonian, or they're different?
So they will have corrections. So you may find that your plaquettes look a little bit weird afterwards, or that you have electric terms on multiple links. But we're allowed to play with the terms to some extent, because the Kogut-Susskind Hamiltonian is not the only possible Hamiltonian that will take you to the correct continuum limit. So we could add larger plaquettes and get away with it.
I want to do another step of this.
Yes.
Would you minimize the same thing you minimized at first, or the new part of the Hamiltonian?
We will do the same procedure again. So we'll minimize again over the plaquettes that we want to have, so to speak.
So the other corrections that are generated in the first step,
yes.
you don't take them into account in this minimization?
No, we won't. In fact, we'll try to correct those errors in an additional step. Yeah.
What do you mean by you're going to use the classical solution to build this? I mean, to me, this control, this operation,
yes,
it's completely defined, right? Without reference to anything else. It's
well, so these A's are the classical solution.
But I thought that these are referred to what edges are being acted on. This is the group element by which we're rotating. So it's not.
So I haven't labeled these new links actually. So, but yes, this L will act on. Let me just check. Oh, that's the target actually. So this L will act on this guy and this guy. No, this L will act on this guy. This next L will act on this guy, and so on. But the A's are functions of the original external edges. So they're functions of the U over which we're integrating here, which are the position bases for these external links. And the functions are defined by this classical solution.
Okay, so you have some information that you introduce.
Yes.
You have this is part of your variational answers.
Yes. This is okay. This is the key.
It's not a variational answers.
Yes, exactly.
But still, you're making a choice.
Yeah, this is the key part of this ansatz, really. This using the classical interpolation here to build in these new links and fine-grain the plaquette. This is the key step.
So if this was the discrete setting,
yes.
Would you know what choice you are making there?
If it a discrete gauge group.
If this was target code, Z2.
Yes, I suppose so.
So you would still have degrees of freedom to play with. That's not something that the theory can consider.
Would you have the degrees of freedom? I think. Yeah. Well, so well, there's not as much averaging to do. Maybe it gets a lot simpler in the Z2 case. And
I do not remember many options.
Yeah, I guess there won't be many because you only you can't do infinitesimal rotations, and so the averaging will be really simple.
I'll ask you later.
Okay.
So in the U1 case,
yes.
after doing this operation, what does the new state look like? Does the flux in the big flux preserve? Is flux preserved?
I thought it was divided.
Yes. So yeah, exactly. So if in the U1, the flux around this plaquette here, or going through this plaquette, should be roughly equally divided among these, but it can get smaller as well. So we're not trying to preserve it.
Or net flux is not same.
No, it needn't be the same. No. We're trying to minimize it. So we're trying to reduce the flux ultimately to zero. But we can only minimize it to a certain extent in each step while maintaining gauge invariance. Is that right? I think that's right.
So A0, A1, A2, A3 are the gauge field in the external link.
A0, 1, 2, 3 are the solutions to this classical interpolation problem. So these, okay, I should have labeled these, I guess. So these external links are labeled by U's, U1, U2, U3, U4, U5, and so on. And we're integrating over those. And these A's are functions of those, given by this classical solution from the previous slides. Okay. All right. So this whole operation is, of course, an isometry. So we're adding degrees of freedom, and we're performing unitary operations on the whole state. And each application of this isometry is the idea, takes us a step closer to the continuum because it minimizes this magnetic term, takes us towards weak coupling. So what we've got is, you can view as a mirror tensor network. So we're starting at the top in this strong coupling state, which is a product over these links. You can imagine this being translation invariant. We're applying this isometry CV once, and we get a new state, a fine-grained state, where the curvature is reduced on each of these subplaquettes, and we do that again and again and again until we want to stop. And we hope to be able to, and because these operations of fine-graining for each plaquette are local operations, we're performing products of local operations, this remains a contractible tensor network, and we can calculate things. So we can do this in higher dimensions too. It's not limited to 2 dimensions. So we can define a fine-graining operation for a cube. We can use the fine-graining operations in 2D that we just had to build those up, for example. So we can do a fine-graining on this face, on this face, on this face, and then we have to worry about the middle. But you can do this. You can solve the classical problems associated with these fine-graining operations, and then you can apply it in the quantum case as before. So yeah, we've argued that the difference to this post-fine-graining state between this post-fine graining state and an exact ground state of the Kogut-Susskind Hamiltonian for some value of the coupling dependent on the number of applications of this isometry is small. But there will be errors, as we've said, and maybe this is an issue, perhaps due to this roughening transition, which may occur at some point. So is there a way of repairing these errors? Well, we could try an adiabatic correction step. So this is possible because we can keep track of the Hamiltonian as we do these fine graining operations, as has already been suggested. Yes?
So just when you say it becomes small, do you have any bounds in mind in regards to the number of steps performed?
Before you get somewhere interesting. Well, okay, so it depends what you want to do.
What can you prove or nothing?
So if you're going towards the continuum with this, and you can calculate things at each step, then let's say you should be able to calculate local expectation values and correlation functions efficiently because of this locality. So if you can do that, and you can do that for a few different values of the coupling as you approach the continuum, then you can hope to extrapolate to the continuum, for example. It's one thing you could do. Yeah. How many steps you take then depends on, well, depends on how many you can practically do and how many gets you the result you're looking for, I suppose. So yeah, we haven't really looked at the limitations of that in terms of how many steps you can take yet.
Were you asking about errors that may accumulate over iterations? Is that what you were asking?
Well, I'm just asking about the distance between those two states, the ground state of the full Hamiltonian and this variational state.
But what's the full Hamiltonian? Do we have is that full Hamiltonian simply the original one just shifting the G, the coupling?
That's the one we're targeting, yes.
And is it clear that what you are obtaining is related to the ground state?
Yes, this is the argument with minimizing the second term of that Hamiltonian.
No, that's the argument, but can you qualitatively assess whether that...
Well,
that's happening?
Qualitatively assess that it's happening. Well, yeah, okay. If something really, yeah, to some extent, yes, because there's certain expectations you have as to how things should behave as you, for example, that there shouldn't be another phase transition until you get to zero coupling, or that this roughening transition should occur. Those are checks you could do. You could also, but okay, yeah, there are probably other things you could do, but I'm not sure right now. But one thing you can do, of course, is attempt to correct these errors after each step, and then you're as close as you can get to the exact ground state again.
But in the end, you have some wave function that you believe that might be a good approximation to the ground state of a Hamiltonian that you also have.
Yes.
So you could ask whether that wave function is an eigenstate of the Hamiltonian.
Yes. Yes.
And
yeah, it might be possible to check that.
The value of the energy has fluctuations.
Yeah, is it easy to, yeah, it should in principle, yeah, why not? Yeah, sure. Yeah, that sounds like a very sensible answer. That's what I should have said, yeah. Okay. Okay, so yeah, so we hope to be able to do a correction step by keeping track of the Hamiltonian as we do this fine graining operation. So in tensor network language, we're keeping track of the parent Hamiltonian for our tensor network, for the layer of the tensor network. So how do we do this? Well, we just introduce terms when we tensor on additional degrees of freedom. So if we add these dangling links in the momentum zero state, we add terms which force them to be in that state. So the state remains a unique ground state of the modified Hamiltonian. So the electric field term, the kinetic term, achieves that for these dangling link states. And then, of course, we apply the parallel transport operation to build them into the lattice and to subdivide these links. So the Hamiltonian gets modified by that unitary, which will spread these terms a little bit, but only a limited amount because these are local operations. Okay, for the loops which we add on here, we said they should be in the position eigenstate of the identity operator. This turns out to minimize the resulting curvature. And to do that, we can just add plaquette terms for those loops. And when we perform our controlled interpolation operation, those will again get spread out a little bit, but again, only a certain extent. So there's a maximum range of these operations determined by the nature of these unitaries we're applying. So now we know, okay, so H prime is the parent Hamiltonian now after a fine graining step. Now we can try and find a path back to the Kogut-Susskind Hamiltonian for a new value of the coupling. So we take our Kogut-Susskind Hamiltonian for some G prime, and we say the parent Hamiltonian is a perturbation of that. Okay. And then we can define a path of Hamiltonians, Ks, which take us back down, and we want to do adiabatic evolution to get the state back to the ground state. What we actually do is approximate the adiabatic evolution necessary using quasi-adiabatic continuation, which you can read about in these papers here by Bachmann, Mikalakis, Nachtigall, Sims, and there's some other papers here which discuss this. This is an approximately local operation. So there will be long-range tails, but they're exponentially suppressed in a finite quasi-adiabatic evolution step. So we're basically local still. So we don't destroy our contractible mirror structure by doing this. And if that all goes well, then we're back in the ground state for the Kogut-Susskind Hamiltonian. Of course, we're making some assumptions here. So we're kind of conjecturing that the state after the fine graining step really is close enough to the ground state that this is achievable. And we're conjecturing also that H prime, the parent Hamiltonian after fine graining, is in the same phase as the Kogut-Susskind Hamiltonian for a smaller value of the coupling. Okay, but we have reason to believe this should be the case. Refer back to previous arguments. Okay, so what properties have we got then for this ansatz? Okay, it is manifestly gauge invariant. That's clear because all the operations we've done have preserved the gauge invariance. It's a contractible tensor network. Slightly less concretely clear, but okay, I think it's reasonable because quasi-adiabatic continuation is effectively local, and the fine graining steps are definitely local. A Lorentz invariant continuum limit, well, if we really can follow Kogut-Susskind down to the continuum, then this should be the case because the limit of the Kogut-Susskind Hamiltonian is indeed the correct continuum limit. So we're kind of stealing that argument from Kogut-Susskind there. And the errors that we make for each fine graining step should be correctable by this adiabatic step. Okay, this is perhaps the vaguest part of this ansatz so far, but it could work, right? So the plan, what are we going to do with this? So we wish to be able to carry out analytical calculations for QCD at low energies. Maybe using perturbations, maybe not. So for pure Yang-Mills theory, we'd like to be able to see that the correlation functions behave as expected, that Wilson loops scale with the correct perimeter or area law. Perimeter law, I guess. Perimeter law. Sorry? Area law. Ah, excuse me. Yes, although it's not the same area law as we normally mean in condensed matter physics. We want to, okay, we should be able to look at this whole setup with fermions, and we can do so while avoiding the sign problem because we're using a quantum state here, and we're not doing Monte Carlo sampling or summing over Feynman diagrams or anything like that. And we should be able to look at dynamical properties for similar reasons. So let's say we have a state at some level of zoom, and we perturb it locally with some operator, like say some Wilson loop related operator, and we say this is our ansatz for an excitation. We can boost it to momenta on the lattice, and we can hope to determine a dispersion relation for those for these excitation ansatzes. And if you can see, for example, then that the dispersion relation is compatible with Lorentz invariance, then you've also got another argument that the ansatz goes to a correct continuum limit. Yeah, okay. And at the bottom, prove confinement. Well, okay, that's a real long shot, but yeah, you never know. Maybe
it's already built in because you start in the start to the limit, or at least confined.
Yes.
Well, okay, yes.
You have to show that it doesn't disappear.
Yes, exactly. Yeah,
But
yeah.
can I ask a question? At what point was the non-abelian nature important? So you should get the data function at some point.
Yes. Yes, yes.
So if you did the same thing for U1,
yes,
would you actually prove that there is a continuum limit?
That there is
It's non-trivial?
that there's a non-trivial continuum. So in U1, you expect a phase transition at some point, right? Before zero coupling.
Yeah.
And well, yeah. So you won't. You're not approaching QED for that reason. So you're in the confined phase, and you're going to approach some other continuum theory. If you do it in that case, if you wanted to do QED, you want to start at the weak coupling limit, I guess. If you want to do U1, but at least it's believed that in non-abelian case, then there's only this phase transition at zero coupling, and then you're okay with doing this renormalization. You'll stay in the same phase if all goes well. Yeah. Okay, any other questions at this point? Yeah?
So, can you go back one time?
Yes.
So, I see some things, some of them are very clear, some of them are not so clear.
Yeah, it kind of goes from top to bottom, I guess.
So, right. So, when you say you still have a contractible tensor network even after these corrections, so these are adiabatic,
yes,
quasi-adiabatic
yes,
transformations that are quasi-local.
yes,
So, adiabatic transformations which are quasi-local.
yes, yes.
So, why do you need the whole meta thing? I mean, why don't you stick to that? You know, you start with your Hamiltonian with a strong limit, a strong coupling limit.
Yes.
And now you should apply one of these adiabatic transformations which don't remove locality.
Yes.
And try to match to get an effective Hamiltonian that corresponds to a weaker coupling.
Well, I suppose so. Okay. It should be possible to do something like that, but I'm not sure how far you would get. So each time you do, so you of course need the state you're at to be sufficiently close to the target state you're interested in. And if you only go for a very small change in the coupling, if you're already at some finite coupling to start with, however you get there, then presumably you could do this, but you would presumably also need a lot more layers to get to the same point.
Layers?
Layers of the network, so you would need a lot.
No network, no network.
Oh, okay. Okay, okay. Well, I mean, it kind of naturally forms a network anyway.
But that already allows you to apply RG, right? In a sense, or it's a fine graining. You could regard it as a fine graining procedure as well.
I suppose. Because if you're getting closer to a state with a lower coupling, then in that sense it's yes, fine graining, yes. But presumably, in order to get to the same effective coupling, you would need to do a lot more of these steps than you would if you do the fine graining steps as well.
Do you regard the fine graining step, this fifth step, as an accelerator?
Yes, I suppose so. Yeah.
And then you just want to correct for.
Now that I try to answer your question, yes. So we also originally considered just doing this fine graining step, right? Which also might be okay, but it's nice if you can correct the errors too. But yeah, I think that's the best answer I can come up with at the moment. That would be more efficient. You would require less layers. Okay. Any other questions right now? Yes.
So back to this U1 phase here. So presumably in 2+1D, there is no phase transition as you tune the coupling constant, and your ansatz should work.
Yes.
So have you ever tried your ansatz and comparing them with, let's say, Monte Carlo results?
Not yet. No. It's so we had this has not yet been done. There's a lot of stuff still to do. So you could do this for a simple 2+1D graph, and that's one of the things on the to-do list to some extent. So there's a really simple setup which you could easily look at and compare even numerically this fine graining ansatz with some other numerics. it's kind of an effectively 1D system, which is still non-trivial. It's a graph of. So if you look at this thing, and you couple these loops with a nearest neighbor plaquette term that goes like this. Then this is non-trivial. This is and you can solve it as a one-dimensional system. You could apply DMRG to this, and you could compare an ansatz of the one we're looking at here, of the type we're looking at here, and see how well it works. I guess there are other settings in which you could do that too. But there's a lot of work still to be done. This is kind of the plan, the direction. And this is maybe a good point to mention that this project is in fact open source and open to contributions. So Tobias has put these papers, the LaTeX source, on a GitHub repository. You can, and he's set up a few simple rules for contributions. It's really easy. If you make a contribution which is more than just spelling or grammatical errors, then you'll go on the author list. The author list will be alphabetical in the final publication. And yeah, you can if you're familiar with GitHub. So if you're familiar with GitHub, you can go on that. You can fork a project, which gives you a copy of it. You can then push changes back to the original project, and they will be accepted unless they're totally crazy, presumably. Yeah. So yeah, that's more or less what I've got. So thanks for your attention, and yeah, a little summary at the end here, and a little advertisement for Evo MPS. Yeah. So thanks very much.
So we are a bit late of time. There were many questions. If there is any urgent questions, please go ahead. Otherwise, I just here until Thursday night.
Yes.
Thursday afternoon. Yeah. So use the Google Calendar if you want to make an appointment with me. Any urgent question? If not, let's thank Ashik.
Thanks for pointing out the margin.